Are you able to see the screen?
Yes, sir.
Okay. Okay. So in the previous class, we spoke about oscillator circuits, right? Uh, we spoke about the condition for oscillation, okay, and we also derived an expression for loop gain for an oscillator circuit, right? Just to quickly recall, oscillator circuits works on positive feedback level, and that's the reason the loop gain AF becomes A divided by 1 minus A beta. Okay, so A beta is called as the loop gain, and AF is called as the overall gain of the uh, oscillator. Okay, now this A beta plays very important role in obtaining the oscillations. Okay, so if A beta is equal to 1, we would say that magnitude condition is satisfied, and with which you can get Vi is equal to Vf, right? Because Vf, as you can see here, Vf is A beta into V naught. Okay, if A beta is 1, your feedback signal becomes output signal, and your feedback signal then it becomes Vi itself. Okay, so in case of oscillator circuit, you don't require any external input signal. Okay, in the absence of external input signal, okay, the moment when we power on the circuit by connecting the circuit to a DC power supply, we get something known as power transients. Okay, and this power transient basically causes um, you know electronic noise or random noise in the resistors. So noise is a bidirectional signal, and this noise is then subjected to a loop gain, I mean the closed loop gain of almost infinity. So a microvolts of noise is then amplified to a volt level using the very high gain of the positive feedback network. And by adjusting the feedback factor beta, the noise signal later on can be shaped to a sinusoidal oscillations. Okay, I mean, to that matter, even any other oscillation is also fine. I spoke about sinusoidal oscillation because in this particular module, we'll be talking about only sinusoidal oscillations. Okay, so that's how basically the oscillator circuits work. Okay, in the absence of input signal, the oscillator circuits can produce waveform. That's the reason it is also called as wave generation circuit or regeneration circuit. Okay, and it can also be called as an inverter circuit because the power input what you require is DC, and the power output what you get is AC. So basically, you are doing kind of DC to AC conversion, hence it can also be called as an inverter circuit. Okay, fine. Now in the previous class, we just spoke about one condition. Okay, that is the magnitude condition as well as the angle condition. If magnitude condition is satisfied and angle condition is satisfied, we say that the circuit results in sustained oscillations, right? Fine. Now let us see more about this magnitude and angle condition. Okay. Okay. Fine. If A beta is equal to 1, what kind of waveform you are going to get? If A beta is equal to 1, you will get sustained oscillation waveform. So that probably I can show something like this. This is your output and this is your time axis. Okay. If A beta is equal to 1, your oscillations will be a sustained one. And it goes on. That means to say it will have a constant amplitude. Okay. It will have a constant amplitude of V max in the positive direction and V minimum in the negative direction. Okay. And this is what is required for oscillation. A beta should be equal to 1. Okay. On the other hand, what if A beta is not equal to 1? Let's say mod A beta is greater than 1. If mod A beta is greater than 1, then the wave nature slightly varies. Okay, the wave nature becomes something of this kind. So in this case, what happens is that the amplitude, okay, keeps on growing. Amplitude keeps increasing. Amplitude keeps increasing. Okay, so it will not result in useful waveform. Okay, but we need a proper sinusoidal waveform. But A beta is greater than 1 leads to this particular scenario. Okay, so basically your waveform is useless. Okay, you cannot use it for any practical applications because amplitude is increasing in nature. And what if the amplitude is greater than the maximum signal handling capacity of the circuit? The circuit may break down because of the excess, voltage. Okay, so this is of no good use. That's the reason. If you get such a condition in your circuit, what will you do is you will vary. Okay, will vary. Okay, I will write. We will vary beta to arrive at mod A beta is equal to 1 condition. Okay, this is what you are supposed to do it in your laboratory. If you find that your waveform is increasing in nature, start varying the parameters of feedback network until you get a waveform of this kind. Okay, we will perform in the laboratory, don't worry. Okay, the third condition is the opposite condition. What if the mod A beta is less than unity? If mod A beta is less than unity, then your output, will be of this kind. This is your output. Since mod A beta is less than unity, okay. Okay, the eraser is not working, no problem. So as time tends to infinity, what happens is that the amplitude, as you can see, keeps on reducing. Okay, the amplitude of the circuit keeps on reducing one cycle after the other. Okay, eventually when time t becomes very large, what happens is that amplitude reduces to 0. So this is also not required. Okay, we want the waveform to be present, but instead, by maintaining a beta less than 1 condition, basically the waveform is going to get vanished after some interval of time. Okay, so this condition should also be avoided. So whenever in the oscilloscope, if you see a straight line, that's an indication that the oscillator is operating under this particular condition. Even when this happens, what you have to do is that we need to vary beta to arrive at a beta is equal to 1 condition. Okay. All right. So this is the effect of loop gain on oscillator output waveform. Okay. So we discussed about 3 factors. Mod a beta is equal to 1. A beta is equal to, a beta greater than 1 and less than 1. Okay. All right. Fine. So now let us talk about the oscillator circuits. Oscillator circuit. Now we'll be discussing about different oscillator circuits. Okay. First, we will start with low frequency oscillator circuit. Which is also called as audio frequency oscillators. Okay, followed by radio frequency oscillator. In short, it is called as RF oscillators, and in short, it is called as AF oscillators. Okay, RF oscillators. And finally, we will study about crystal oscillator. Crystal oscillator. Okay. Now, audio frequency oscillators up to few. Okay, let's say up to 100 kilohertz. Okay, this is up to several hundreds of kilohertz. Okay, in fact, maybe up to megahertz also. Maybe up to few megahertz. That's your radio frequency oscillator. And finally, crystal oscillator. It is very high frequency. For very high frequency waveform generation, you can go for crystal oscillator. The typical frequency is greater than megahertz. Okay, the starting frequency itself is in megahertz of range. Okay, on the other hand, in case of radio frequency oscillator, the starting frequency will be in several hundreds of kilohertz. So that's how the oscillator circuits have been classified. Okay, low frequency, mid frequency, and extra high frequency. Okay, now under low frequency oscillator, okay, we have 2 types. And in radio frequency oscillators, we once again have 2 types. And in crystal oscillator, we are going to have 2 types. Okay, so basically you will have total 4 oscillator circuits to study. Okay, fine. Let's start one by one. Okay, and remember one thing: in all these oscillator circuits, we will be considering only transistor-based oscillators. Okay. There are operational amplifier-based oscillators, but we are not going to talk about operational amplifier-based oscillators because those oscillators are studied in 4th semester in a subject called linear integrated circuits. All right. So first oscillator circuits let us study, which is falling under audio frequency oscillator category, and that is RC phase shift oscillator. RC phase shift oscillator. Okay, so first let me write the circuit diagram. Now, before actually constructing the circuit diagram, let me propose the generic circuit diagram. Now, in case of oscillator circuit, see, in the preliminary discussion, I have spoken about it. Okay, that is, an oscillator circuit is consisting of an amplifier block and a feedback network. Okay, so the oscillator circuit is consisting of two major blocks, amplifier blocks and feedback block. Okay, now this amplifier block is made up of RC elements, or amplifier is RC coupled amplifier. Amplifier is RC coupled amplifier. So everywhere, in all the 6 circuits, we will be considering the same amplifier circuit, which is RC coupled amplifier circuit. Okay. What differs in an oscillator circuit is that the feedback circuit. In every oscillator circuit, you will have different feedback circuits. Okay. You will have a different feedback circuit for RC phase shift oscillator, and you will have different feedback circuit for radio frequency oscillator. Okay, so amplifier remains the same. On the other hand, feedback network varies. Okay, so depending upon the need, you will have to go on changing the feedback network. Okay, all right then. So first, let us construct the circuit diagram. Okay, so first let me construct the amplifier block. Okay, so the amplifier block is consisting of transistors, okay, the biasing resistor, collector resistor, voltage divider circuit, okay, the power supply, VCC, and this is your transistor Q. Remember one thing, there is no input, okay, because it's a oscillator circuit. So this is the common mistake what normally students, they do it in the exam. Okay, remember, there is no AC input for oscillator. In spite of that, student tend to write VI over here, and because of this, the entire circuit goes for a toss. Okay, you cannot have an input signal for an oscillator circuit. If you write an input signal for an oscillator circuit, trust me, you will be given with 0 marks because your concept becomes wrong. Okay, so don't ever write VI for an oscillator circuit. Fine. So we are done with the oscillator circuit. Yeah, except for the coupling capacitances. This is your output coupling capacitance, and this is your bypass capacitor CV. And you also have an input coupling capacitance, let's say CI. So amplifier block is done. Now what we have to do? Now we need to draw. Okay, let me write with a different color. That this is your amplifier block. Okay, let me change the color. Now let me construct the feedback part. Okay, so for the sake of clarity, what I will do is I will shift the feedback block in the downward direction. Okay. Okay. So the feedback block is consisting of passive elements consisting of resistors and capacitors. A second capacitor and a third capacitor. Okay. The output of feedback network is connected with to the input terminal of the amplifier. Okay. So by doing so, did I connect any VI? No, I haven't connected any VI because in case of oscillator, the feedback voltage serves as the input voltage to the amplifier circuit. Okay. Now, next comes the resistive element. Okay. So other end of resistor is grounded. C, 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 and this is R, R, and R. Okay, let me use a different color for this. Let's say blue color. So this particular network is your feedback network. Is your feedback network. So you have an amplifying network which is made up of, voltage divider by circuit elements, and then you have your feedback network which is made up of three-stage RC element. That's the reason the oscillator circuit is called as RC phase shift oscillator. Okay, why phase shift? Because this single stage of RC elements will introduce a kind of phase shift. Okay, now this RC coupled amplifier offers 180-degree phase shift. Okay, RC coupled amplifier offers 180-degree phase shift because RC coupled amplifier is a common emitter amplifier, right? Emitter is common to input circuit as well as output circuit. In CE configuration, you know that output is out of phase from the input by an angle of 180 degree. So 180 degree is given by the RC coupled amplifier. So what should be the phase shift introduced by the feedback network? Remember one thing, while studying the oscillator principle, we had seen that the angle condition A beta should be 1, right? And the angle of A beta, that is the angle of loop or the total loop angle, should be 0 degree or 360 degree. Now, in order to get 0 degree or 360 degree, what you are supposed to do? You are supposed to introduce further 180 degree phase shift, right? Because 180 degree phase shift is given by the amplifier network. If you can get the further 180 degree phase shift from the feedback circuit, total phase shift, that is angle of A beta, becomes 180 degree plus 180 degree, that is 360 degree, which is considered as 0 degree. Okay, so this is how you have to design your feedback network. So you know that a pure capacitor gives phase shift of 90 degree. So if at all you use pure capacitor, then 2 capacitors are enough to introduce 180 degree phase shift. But the problem is no capacitors are ideal in nature. So that's the reason, the phase angle is always less than 90 degree. Okay, greater than 0, but less than 90 degree. That's the reason, you will have to go for more than 2 stage. Okay, 3 stage at the maximum you can go for. Okay, you can go for 4 stage, but the elements will increase, right? The size of the network will increase. So if not 2 stage, probably you can go a step further and you can consider a 3 stage. So that's the reason 3 stage RC network is used. Okay. Now, what is your ultimate aim? Your ultimate aim is to get 180-degree feedback, right? So you're using a 3-stage RC network. That means to say each stage should give a theoretical phase shift of 60 degree, because 60 into 3 is 180 degree. So each stage should give a theoretical (60°), right? Therefore, the total phase shift is equal to 3 into 60 is equal to 180 degree. Hence, the condition is satisfied. So this is the whole idea of RC phase shift oscillator. Okay, all right. So that's about the phase shift of amplifier block as well as the feedback block. Okay, now let me talk about the explanation. So explanation is pretty simple. You have to just explain the various elements. So under explanation, what I will do is the circuit is consisting of 2 parts. Okay. The first part is amplifier. Okay. So amplifier part is consisting of biasing network. Okay. And what are the elements of biasing networks? Resistor R1, R2, RC, and RE constitutes the biasing network. Okay. Then you have AC elements, CI, C0, CE are blocking capacitors, in bracket CI and C0, and bypass capacitors. What is bypass capacitor? C is the bypass capacitor. Okay. So proper biasing is chosen for faithful amplification. Proper biasing is chosen for faithful amplification. Okay. In a sense, you should have a symmetric waveform, or the Q point should be placed at the center of the load line. So you can say that Q point is placed at the center of the load line. Okay, so that's about the amplifier part. Next, you have the feedback part. We'll write A, and this I will write B. Okay, so feedback part. So feedback part is consisting of, it consists of a 3-stage RC element, okay, which is also called as ladder network. called as three-stage ladder network. Okay. Now, the feedback network introduces phase shift 180 degree. Okay. The question is how? Is there any way to prove that the feedback network introduces phase shift? Okay. Now, to understand the phase shift concept, what we can do is let us consider a single stage. Consider a single stage of the ladder network. Okay. Say this. Okay. Let us say that Vi is the input voltage to the ladder network. This is C and this is R. What we have done, we have just considered a single stage of the ladder network. Okay. So we have C and we have R. This is the input, and across the resistor, whatever you get the voltage that is assumed as the output. Okay. So voltage across the resistor, let us take it as VR, the resistive voltage. And voltage across the capacitor, let us consider it as VC, the capacitive voltage. Okay. And let us say I is the RMS value of the charging current. Okay. Since it's a RC network, what we can do is we can construct a phasor diagram. Okay. So to construct the phasor diagram, okay, what I will do is I'll consider the circuit current as the reference. So I is taken as reference. Okay. Now you have two voltages. Basically you have three voltages, VI, VC, and VR. The vector sum of VC and VR should give you the input voltage VI. So what I meant to say is vector VI is basically vector VC plus vector VR. So vectorically, if you add the capacitive voltage and the resistive voltage, you will get the resultant voltage. Okay, fine. So what's the phase relationship between resistive voltage and current? Resistive voltage is always in phase with current, right? And what is a phase relation between capacitive voltage and current? The capacitive voltage always leads the current by an angle 90 degree. So this is VC. So the angle separation is 90 degree because VC leads current by an angle of 90 degree. So the closing side of the triangle basically gives, the resultant. So this is VI. Okay. The angle between VI, I'll put in I will designate the vectors with star. The angle between VI and I is taken as phi. So angle phi is the phase shift. Is the phase shift between the input voltage and the circuit current. Now, in order to find an expression for phase shift, you can make use of trigonometry. What you can do is you can, write tan phi. So tan phi is basically y by x, right? So along y, what have you projected? You have projected VC. And along X, what have you projected? You have projected VR. But what is VC? I into XC. VR is I into R. So I gets cancelled. So you are left with XC by R ratio. But XC is 1 over 2 pi FC. So therefore, the tan phi, becomes 1 over 2 pi F into R into C. That implies phi is equal to tan inverse of 1 by 2 pi FRC. Okay. So by properly choosing R and C value for a particular F value, where F is the oscillator frequency, remember, oscillator frequency, phase shift phi can be designed. So this is how we fix the value of phi. Okay. So in short, you can find phi as tan inverse of XC by R, or you can substitute the XC expression, and then it becomes 2 pi FC into R. Okay. So this is the theory behind the phase shift. Okay. So this is how we design the required phase shift for a RC phase shift oscillator circuit. Okay. Any doubts till now?
No, sir.
Fine. Okay. Next, waveforms. If I start drawing everything in this particular graph, it looks very shabby. So what I will do, first I will mark the voltages, okay, at the particular locations, and separately let me draw the waveforms. Okay. So the voltage, okay, measured from this terminal to ground is called as the output voltage. This is your output voltage. On the other hand, the voltage which is measured from the last resistor will be your feedback voltage. Okay. So I think in a small scale I can draw. So let's say, for example, okay, this will have a better visibility probably. Okay. Let's say, for example, you apply, okay, voltage of this kind. Okay, so this is your basically the input voltage. Okay, not the external voltage. Remember, this input voltage itself is VF, remember, because there is no element connected in between and there is no physical input. Okay. Just for the sake of representation, I have considered VI. So VI is considered from the capacitor terminal to the ground terminal. So let's say VI is positive going. Okay, so this Vi is coupled to the base terminal of the transistor through the coupling capacitor Ci. So the output voltage V0, whatever you get, will be a phase inverted one. Okay, will be a phase inverted one. Why phase inverted? Because the amplifier what you have chosen is a common emitter mode amplifier, which introduces 180-degree phase shift between the input Vi and the output V0. Okay, so when this inverted output, okay, when this inverted output is fed back to the feedback network, remember the same V0 here you are going to feed. Okay, you can see, right? The V0 signal is coupled back to the feedback network. So this V0 is getting applied across this network, and due to which what happens? Feedback signal VF is generated. And what is the phase shift between VF and V0? It is once again 180-degree. So when you give a negative going signal to the input of the feedback network, at the output of the feedback network, you will get a positive going signal. So this is VF. Okay. So there is 180-degree phase, right? See, here you have negative going half cycle, but at VF terminal, I mean at this terminal, you will have a positive going signal, and that is because of the 180-degree phase shift introduced by the RC element. Okay. Now you compare the phase of VF and VI. See, so your VI always matches with VF. That's because VF itself is connected back to the base terminal of the oscillator circuit, and that is how the feedback is fed back to the input terminal of the transistor. Okay, so this process repeats one cycle after the other, and you will get a constant sustained output waveform across the output coupling capacitor C0 and across the ground reference. Okay, so this is how the RC phase shift oscillator is going to work. Okay, fine. So that's about the waveform I have already drawn. Next, the expression for frequency. Okay. Now, in the expression for frequency, basically derivation is there. So derivation will be done in the later half of the module. Okay. In the end, I will do the derivation. So derivation will be done at the end. Okay. So I will not forget it. I'll do it, but in the end, I will do it. Okay. Now let me go with the flow. Now, when you apply, say, mesh analysis, because there are three loops, right? There are three loops here. See, you have loop 1, loop 2, and loop 3. So basically, we go for mesh analysis to carry out the derivation. You would get the frequency of oscillation F is equal to 1 divided by 2 pi RC under root 6 plus 4k. Okay, so this is the expression for frequency of RC phase shift oscillator, where R is equal to resistance of ladder network. What is ladder network? The feedback network. Okay, and the resistance of ladder network. C is equal to capacitance of ladder network. Okay, and K is basically the ratio of the resistance. Ratio of RC by R is taken as constant value k, because ohm by ohm is dimensionless, right? So k is the ratio of RC by R. Okay, so this is the expression. Okay, we will do it in the end. Okay, fine. So that's about your RC phase shift oscillator. Now, condition for oscillation. Condition for oscillation is that the HFE of the transistor, okay, HFE of the transistor should be greater than or equal to this series 4K plus 23 plus 29 by K. Okay, so for problems you need to by heart this. Okay, but there is a derivation. Okay, so frequency of expression can be derived, as well as this condition can also be derived. Derivation I will do it in the end. Okay, so HFE, that is the transistor gain, current gain, if it is greater than or equal to this particular series, then only the circuit results in oscillations. Okay, if at all your transistor current gain is less than the right hand side value, then no matter what you do, the circuit will not give you any oscillations. Okay, fine. So that's about your RC phase shift oscillators. Okay, advantages. Okay, the major advantage is that simple construction. Okay, then it produces, or rather it produces output in the audio frequency range, in short EAF range I will write. Okay, then less costlier because it uses inexpensive elements. Okay, and it gives sinusoidal output. Okay, gives sinusoidal output. So these are the major advantages. Okay, and you can also say that very light and compact. And since it is consisting of less elements, can be fabricated in the form of an IC. Okay, so instead of taking discrete resistors and capacitors, for a particular frequency, you can even think of fabricating the entire oscillator circuit in the form of an integrated chip. Okay, fine. So these are the advantages and disadvantages. Okay, the first disadvantage is that variable frequency operation is not possible. Okay, why variable frequency operation is not possible? In order to get the variable frequency oscillation, what we have to do is we have to simultaneously vary the ladder network elements. That means to say, simultaneously you have to vary the 3 capacitance values, or simultaneously you have to vary the 3 resistance values. So variation of 3 elements simultaneously is impossible to achieve. That's a reason it is considered as a fixed frequency oscillator circuit. Hence, variable frequency is not achievable. All right, so that's the first disadvantage. The second disadvantage is that the operation is affected by external factors such as temperature, aging factor, etc. Okay. Now, what is these? What are these external factors? Temperature, you know, right? Resistance depends on temperature, right? When the temperature changes, the resistance value changes. Okay, and you can see that in the expression of frequency. Your frequency is inversely proportional to resistance. So when this resistance R changes due to temperature change, the frequency will change. Okay, so there will be a drift in frequency if there is any difference in temperature. Okay, and aging. Okay, aging is something like any physical device is prone to aging over a period of time. The resistance value of 1 kilo ohm, okay, may not be the same when you measure the same resistance value after few years. Okay, the resistance value may drift from its set value. So due to this drift in resistance and capacitance value, once again the frequency may get affected. Okay, so these are the major disadvantages of RC phase shift oscillator. Okay, all right, so that's all for the day. So what I will do in the next class, that is tomorrow, I will continue with the other oscillator circuits. So tomorrow let us consider the second audio frequency oscillator circuit, which is called as Wien bridge oscillator circuit. Okay, fine. If you have any doubts, you can just ask me. Okay, if you don't have doubts, you can register your attendance and probably you can drop off from the class.